Hello everyone, this is Math with Zinger. Welcome to our AP Calculus BC series. Now we're moving into 1.2 Applications of Limits. In this section, we will cover three main applications of limits: continuity and discontinuity, asymptotes, and intermediate value theorem. We will start with continuity and discontinuity. Here are three common reasons a function may not be continuous. In the first graph, fc is not defined, so there is no actual function value at that point. In the second graph, the limit as x approaches c does not exist because the left and right slices do not meet. In the third graph, the limit exists, but it is not equal to fc. So, for a function to be continuous, the function must follow these three conditions. First, fc is defined. Second, the limit as x approaches c exists. Third, the limit equals the actual function value. So, the limit as x approaches c equal fc. If all three conditions are true, the function is continuous at that point. Let's look at an example. The open circles shows places where the function is not defined at the exact point, while the filled dots show the actual function values. When checking continuity, we compare the limit with the function value. For example, if the graph approaches one y value, but the filled dot is somewhere else, then the function is not continuous there. So this function helps us see that continuity depends on both the limit and the actual value of the function. And we will introduce three discontinuity. The first one is called removable discontinuity. A removable discontinuity usually looks like a hole in the graph. The limit may still exist because the graph approaches the same value from both sides, but the function is not continuous because the point is missing or the function value is placed somewhere else. It is called removable because we could fix it by filling in the correct point. The second one is called jump discontinuity. A jump discontinuity happens when the left-hand limit and the right-hand limit are different. In other words, the graph jumps from one y value to another. Because the two sides do not approach the same value, the limit does not exist at that point. So a jump discontinuity cannot be fixed by just filling in one hole. And the last one is infinite discontinuity. An infinite discontinuity happens when the function goes up or down without bound near a certain x value. In this example, y equal to 1 over x squared grows toward infinite as x get close to 0. This usually happens near a vertical asymptote, so the function is not continuous because the values become unbounded. Properties of continuous functions. This theorem tells us that continuous function stays continuous under normal operations. If f and g are continuous at x equal to c, then their sum, difference, product, and constant multiples are also continuous. Their quotient is also continuous as long as the denominator is not 0. This is useful because it lets us build more complicated continuous functions from simpler ones. Now, let's move on to asymptotes. Here we have an example. In this graph, we can see two asymptotes. The vertical asymptote is x equal to -2. Near this line, the function goes up or down very quickly. The horizontal asymptote is y equal to 1. As x goes far left or far right, the graph gets closer to the horizontal line. So, vertical asymptotes describe behavior near a certain x value, and horizontal asymptotes describe end behavior. And here is the definitions of vertical and horizontal asymptotes. A vertical asymptote happens when the function approaches positive or negative infinity as x approaches a certain number. A horizontal asymptote happens when the function approaches a fixed y value as x goes to positive or negative infinity. So vertical asymptotes use infinite limits and horizontal asymptotes use limits at infinity. Another example, the graph shows the exponential function y equal to e to the power of x. As x goes to negative infinity, the graph gets closer and closer to the x-axis. That means y equal to 0 is horizontal asymptote. The graph never actually becomes 0, but it approaches 0 as x goes further to the left. So this is another example of how limit described end behavior. And the last one Intermediate value theorem. The intermediate value theorem says that if a function is continuous on the interval a,b, then it must hit every y value between fa and fb. So if y0 is between fa and fb, then there must be some c between a and b where fc equal to y0. The graph shows this idea. Since the curve is continuous, it cannot jump over the value y0. It has to pass through it. That's everything for 1.2 Applications of Limits. Thank you for watching. Please follow for more.